Hello everyone, this is the GATE topic solid state physics, and today we will talk about the question from GATE question paper 2016, and the question number is 15. So what is the question? A one-dimensional linear chain of atoms contains two types of atoms of masses m1 and m2, where m2 greater than m1 arranged alternatively. The distance between successive atoms is the same. Assume that the harmonic approximation is valid. At the first Williamson boundary, which of the following statements is correct? And there are four options. The options are: the atoms of mass m2 are at rest in the optical mode while they vibrate in the acoustical mode. The option number B is: the atoms of mass m1 are at rest in the optical mode while they vibrate in the acoustical mode. Option number C is: both types of atoms vibrate with equal amplitudes in the optical as well as in the acoustic modes. And option number D is: both types of atoms vibrate but with unequal non-zero amplitudes in the optical as well as in the acoustical modes. So for that case, we just need to see two things. First of all, they are telling our M1, M2 is greater than M1. This is the first condition we have to check, and the second condition what we have to check, that they are asking at the first Williamson boundary. This condition they are telling. So what will happen at the first Williamson boundary? I mean, like M2 will be at rest in optical mode, or M1 will be at rest in optical mode, or both type of atoms will vibrate with equal amplitudes in the optical mode, or both types of atoms vibrate with unequal amplitude of optical mode. So this type of four options were there. So for that case, what we will do, we will first draw a picture. So you can see here, this is k values. Actually, this is nothing but the EK diagram, right? So for that case, what we will see, when this type of one-dimensional atomic cases will be there. So let's say this is our first Williamson, that means pi by 2a, and it is minus pi by 2a. So what will be the nature of the plot? It will be like this type. It will come as like that, and then from here it will be like that. So you can see this is the boundary of the first Williamson, and again this is also the boundary of first Williamson. So now what does this explain? This is nothing but acoustical mode, and this is optical. Okay. So here there are two omega values are coming, right? So for this case, if you just see the theory of this type of a diagram, then we can find the theory will be like having omega 1 is equals to root over 2 beta divided by m2, and for this case it will be, let's say, omega 2, which will be root over 2 beta divided by m1. Not exactly here, it will be on this point itself. So that means at the boundary of the first Williamson, you can see that for the acoustical mode, the omega 1 will be root over 2 beta by m2, and for optical mode, the omega 2 will be root over 2 beta by m1. Now you can see, and also there were one condition in that case implied that m2 greater than m1. So now for this case, if you see for the optical mode, if I just only focus on the optical mode, in that optical mode our omega 2 is nothing but root over 2 beta divided by m1. So that means in that case our m2 atoms are at rest, right? So in optical mode, M2 atoms will be at rest. Now coming to the options again, the atoms of M2 are at rest in the optical mode while they vibrate in the acoustical mode. Obviously, they will vibrate in the acoustical mode because you can see for the acoustical mode. Okay. So for acoustic mode, our omega 1 was root over 2 beta divided by M2. So that means our M2 will vibrate in the acoustic mode, but it will be at rest in the optical mode. That means the option number A, which one is the first one, is the correct one.